Welcome to Summarize Science, where we break down the latest research. Today, we're looking at a paper that connects two things you'd never expect: charged, rotating black holes, and soap bubbles. It sounds strange, but this analogy helps us understand some of the deepest laws of the universe. The paper is titled Charged Rotating Black Hole and the First Law, and it tackles big questions about energy, entropy, and gravity. Let's start with the analogy. Imagine a simple, spinning soap bubble that has an electric charge. The paper reminds us of a key principle from physics: the farther you move away from this bubble, the less of its charge you can effectively measure. This graph here visualizes that idea for the soap bubble. As the distance d increases, the measured charge q drops off. The bubble's charge becomes a mostly local effect. Now, the researchers apply the same logic to a charged, rotating black hole. And amazingly, they find the exact same thing happens. As an observer gets farther away from the black hole, the charge stored in its surrounding field seems to diminish. This graph shows that as the distance b grows, the measured charge q decreases, just like with the soap bubble. So, why is this important? Because it helps solidify our understanding of black hole thermodynamics. Specifically, it helps confirm that the first law of thermodynamics, a fundamental rule about the conservation of energy, remains valid even for these extreme objects. The paper demonstrates how to consistently include charge in the energy equation for a black hole. This has a fascinating consequence for what we could ever hope to observe. It suggests that from our viewpoint here on Earth, far from any black hole, its charge is essentially a hidden feature. All the complex activity, like entropy production, is confined to a region close to the event horizon. For a distant observer, the black hole's state appears pure and unchanging. This could also help explain why detecting things like Hawking radiation is so incredibly difficult. So, let's recap the key points. This research uses a brilliant analogy with soap bubbles to show that a black hole's charge is a local phenomenon that fades with distance. This reinforces the idea that the laws of thermodynamics apply to black holes, strengthening the connection between gravity and quantum theory. What does this mean for the future? Well, for astronomers observing things like quasars, it means they're likely just seeing the gravitational effects, not the charge effects. However, the charge could still play a huge role in the chaotic plasma dynamics happening right at the event horizon, possibly influencing the powerful jets we see shooting out of galaxies. And the most exciting part is that as our gravitational wave detectors become more sensitive, we might one day be able to pick up the tiny signatures of a black hole's charge. This could open up a whole new window for testing these incredible theories about the universe. Thanks for watching Summarize Science.